This is my 9th video lesson for Unit 13. In this lesson, we'll be calculating the pH of a weak acid or weak base and the percent dissociation. Go to page 40 in the class packet. Learning target. At the end of the lesson, I'll be able to calculate the pH, the Ka, the Kb of a weak acid or weak base, and the percent dissociation. Homework is number 9. Task number 1. Calculate the pH of a weak acid. Question 1. What's the pH of a 0.1 molar solution of acetic acid? We are given the Ka equilibrium constant for acetic acid. The first step is to write out the chemical equation. Acetic acid is a weak acid, therefore there is equilibrium. Since the goal is to figure out the pH of acetic acid, we need to determine the hydrogen ion concentration at equilibrium, so we need to use the Rice table. Let's first write out the Ka equilibrium expression. Next, we're going to fill out the Rice table. The initial concentration of acetic acid is 0.1. Since water is a liquid, it does not belong in the equilibrium expression, so we can leave this blank. The initial concentration of hydrogen ion and the conjugate base of acetic acid is 0 molar each. To figure out the change in concentration, we need to determine which direction the equilibrium will shift. Since the products are 0, equilibrium will shift to the right. So the change in concentration for acetic acid will be minus x. The change in concentration for the products will be plus x. To figure out the concentration at equilibrium, we add the initial concentration and the change in concentration. So the equilibrium concentration for acetic acid will be 0.1 minus x. The equilibrium concentration of each of the products will be x. Once we figure out the value of x, we will know the concentration of hydrogen ion. To solve for x, we will plug in the equilibrium concentration into the Ka expression. To simplify the Ka expression, we can use the 5% rule to avoid using the quadratic equation. We get x as 1.33 times 10 to the minus 3 power, which is the hydrogen ion concentration. Once we get the hydrogen ion concentration, to get the pH, pH is negative log of the hydrogen ion concentration. Negative log of 1.33 times 10 to the minus 3 power gives us 2.88. So the pH of acetic acid is 2.88. Now that we got the pH of acetic acid, what percentage of acetic acid is dissociated into hydrogen ions? We know the initial concentration of acetic acid is 0.1 and the equilibrium concentration of the hydrogen ion is 1.33 times 10 to the minus 3. We can set up a ratio to determine the percentage of the acid dissociated into hydrogen ions. This is known as percent dissociation or percent ionization, which represents the ratio of the concentration of dissociated hydrogen ion to the concentration of the undissociated compound. Here are the equations for percent dissociation for the acid and percent dissociation for the base. So let's say if you have 5% dissociation of your acid, this means that 95% of your acid is undissociated and only 5% of your acid is dissociated, as you can see from this diagram. So let's calculate the percent dissociation of acetic acid. Let's plug in the values into the equation. We know the hydrogen ion concentration is 1.33 times 10 to the minus 3. The initial concentration of acetic acid is 0.1 times 100% gives us 1.33% dissociation. Question 2. What is the pH of a 0.1 molar formic acid solution with a Ka of 1.8 times 10 to the minus 4? The first step is to write out the chemical equation. The next step is to write out the Ka equilibrium expression and then fill out the Rice table. The initial concentration of formic acid is 0.1. We ignore water, and the initial concentration of the hydrogen ion and the conjugate base of formic acid is 0 molar each. Since the initial concentration of the products is 0 molar each, the equilibrium will shift to the right. So the change of equilibrium of formic acid will be minus x, and the change of concentration for the products will be plus x each. So the equilibrium concentration for formic acid will be 0.1 minus x. The equilibrium concentration for the products will each be x. Now we have to solve for x to get the concentration of the hydrogen ion. So we plug in the equilibrium concentrations into the Ka equilibrium expression. To avoid using the quadratic equation, we're going to use the 5% rule. We get X as 0.0042, which is the hydrogen ion concentration. To get the pH, we take the negative log of the hydrogen ion concentration, and we get pH as 2.37. Now that we got the pH, what is the percent dissociation? We plug it into the percent dissociation equation. The hydrogen ion concentration is 0.0042. The initial concentration of formic acid is 0.1 times 100% gives us 4.2% dissociation. Try to do question 3 by yourself. Pause the video. Resume as completed. Here are the answers. Now let's look at an example about calculating the pH of a weak base. Question 1. What is the pH of a 0.1 molar of ammonia? The first thing you want to do is write out the chemical equation. The next step is to write out the equilibrium expression, Kb. Now we got to figure out the concentration of hydroxide at equilibrium. So we have to use the Rice table. The initial concentration of NH3 is 0.1. We ignore water. The initial concentration of hydroxide is 0. The initial concentration of NH4 plus is also 0. Since the initial concentration of the products is 0 molar, equilibrium will shift to the right. Therefore, the change in concentration of NH3 will be minus X, and the change in concentration for the products will be plus X each. The equilibrium concentration for NH3 will be 0.1 minus X. The initial concentration for each of the products will be X. To solve for the value of X, we're going to plug in the equilibrium concentration into the Kb expression. We're going to use the 5% rule to avoid using the quadratic equation. We get X as 1.33 times 10 to the minus 3 power. This is the hydroxide concentration. To solve for the pH, we need to first solve for the pOH. pOH is equal to the negative log of the hydroxide ion concentration. So pOH is equal to 2.88. Once we got the pOH, we can solve for the pH, because pH plus pOH is equal to 14, so pH is equal to 11.12. So what is the percent dissociation of 0.1 molar of ammonia? We know the hydroxide ion concentration is 1.33 times 10 to the minus 3. The concentration of the base is 0.1 times 100% gives us 1.33% dissociation. Question 2. Calculate the pH of a 0.6 molar solution of methylamine. We are given the Kb of methylamine, which is a weak base. The first step is to write the chemical equation of methylamine. Next, we're going to write the Kb equilibrium expression for methylamine. We're given the initial concentration of methylamine to be 0.6. We're going to ignore H2O. The initial concentration of hydroxide will be 0 molar, and initial concentration of the conjugate acid of methylamine is also 0 molar. Since the products are 0 molar, equilibrium will shift to the right. Therefore, the change in concentration of methylamine will be minus X. The change in concentration for the products is plus X each. The equilibrium concentration of methylamine will be 0.6 minus X. The equilibrium concentration for each of the products will be X. To solve for X, we will plug in the equilibrium concentration into the Kb expression. To avoid using the quadratic equation, we'll be using the 5% rule. We get X as 1.62 times 10 to the minus 2, which is the hydroxide ion concentration. To get the pH, we must first solve for the pOH, which is a negative log of the hydroxide ion concentration. pOH is 1.79. To solve for the pH, we do 14 minus the pOH to get the pH, which is 12.12. To get the percent dissociation, it will be the concentration of hydroxide over the concentration of methylamine times 100%, which is 2.7% dissociation. Try to do question 3 by yourself, pause the video, resume as completed, here are the answers. Try to do practice number 1 by yourself, pause the video, resume as completed, here are the answers. For task number 2, we'll be solving for the Ka given the pH. Example number 1, a solution of 0.1 molar of HOCN has a pH of 2.24. Calculate the Ka value of this acid. The first step is to write out the chemical equation of HOCN, which is a weak acid. The next step is to write out the Ka expression. We need to figure out the concentration of H+, OCN-1, and HOCN. To do that, we'll be using the Rice table to figure out the equilibrium concentration. Since we have the pH, we already know the hydrogen ion concentration. Since hydrogen ion concentration will be 10 to the minus pH, which is 0.0058 molar. Using that information, we can figure out the equilibrium concentration of HOCN and OCN-1. Since H plus and OCN-1 are 1 to 1, OCN-1 also has an equilibrium concentration of 0.0058. Since the initial concentration of the products is 0, equilibrium shifts to the right. So the change in concentration of the products is plus 0.0058. So the change in concentration for the reactant HOCN must be minus 0.0058. So the equilibrium concentration of HOCN will be 0.1 minus 0.0058, which is 0.0942. Now that we have the equilibrium concentration, we can plug it in into the Ka expression. Once we plug it in, we get 3.6 times 10 to the minus 4 as the Ka. Let's look at example 2. At a particular temperature, a 1.0 molar of H2S solution has a pH of 3.75. Calculate the value of Ka at this temperature. The first step is to write out the chemical equation. H2S is a weak acid. Next, we're going to write out the Ka expression. We need to solve for the value of the hydrogen ion concentration, Hs minus concentration, and H2S concentration. Using the Rice table, the initial concentration of H2S is 1.0 molar, and the initial concentration of H plus and Hs-1 is 0 molar. Since we're given the pH, we can solve for the H plus concentration at equilibrium, which is 10 to the minus 3.75, which is 0.00018 molar. Since H plus and Hs-1 are 1 to 1, the concentrations are the same. Since the initial concentration of the products is 0, equilibrium shifts to the right. So the change in concentration for H plus and Hs-1 is plus 0.00018. So the change in concentration for H2S must be minus 0.00018. So the equilibrium concentration of H2S will be 1 minus 0.00018, which is 0.99982. Now that we have the equilibrium concentration, we can plug it in into the Ka expression, which gives us 3.2 times 10 to the minus 8, which is the answer. Now try to do the rest of the questions by yourself. Pause the video, resume as completed. Here are the answers. For task number 3, we'll be finding the percent dissociation. Question 1. A solution of acetic acid, where given the Ka, has a pH of 2.876. What is the percent dissociation? In order to solve for the percent dissociation, we need to figure out the hydrogen ion concentration and the concentration of acetic acid. Step 1. Determine the hydrogen ion concentration from the pH. The equation is hydrogen ion concentration is equal to 10 to the minus pH. Since pH is 2.876, the hydrogen ion concentration is 1.33 times 10 to the minus 3 molar. Step 2. Determine the concentration of the acid. We can get the concentration of the acid from the Ka expression. Let's first write out the chemical equation. Next, let's write the Ka equilibrium expression. We know H plus and the conjugate base of acetic acid are 1 to 1, therefore they have the same value. Using that information, we can solve for the concentration of acetic acid, which is 0.1 molar. For step 3, we can calculate the percent dissociation. The hydrogen ion concentration is 1.33 times 10 to the minus 3 over the concentration of acetic acid, which is 0.1, times 100% gives us 1.33% dissociation. Question 2. A generic weak acid, formula is equal to Ha, has a pKa of 4.401. If the solution pH is 3.495, what is the percent dissociation? Step 1. Determine the hydrogen ion concentration from the pH. The hydrogen ion concentration is equal to 10 to the minus 3.495, which is 3.2 times 10 to the minus 4 molar. Step 2. Determine the Ka from the pKa. We know that Ka is equal to 10 to the minus pKa, so 10 to the minus 4.401 is 3.97 times 10 to the minus 5. Step 3. Determine the concentration of the acid. We need to get the concentration of the acid from the Ka. Here's the chemical equation for the generic acid Ha. Next, let's write the equilibrium expression Ka. Since H plus and A minus are 1 to 1, they have the same value. Now we can solve for the concentration of Ha, which gives us 0.00258 molar. Step 4. Calculate the percent dissociation. Now we plug it into the equation. We get the percent dissociation as 12.4%. Try to do the rest of the questions by yourself. Pause the video, resume as completed. Here are the answers. This concludes the video lesson. Remember to do the homework.